lecture number 3, and in this lecture I will be discussing stress strain diagram. So very important topic, basically stress strain diagram for mechanical as well as civil engineering for gate examination. Suppose if you are preparing for gate and you're preparing strength of material subject song, so this topic is very important, not only for the gate examination theory paper, but also for the interview questions also, because whenever after cracking your gate exam, whenever you go for any type of interview, definitely question from this topic will be asked. So very important topic. Okay, now which type of question can come from this topic? So both, either theoretical as well as numerical. So both theoretical as well as numerical can come from this topic. So we should be prepared for both. So I will be covering all. Okay. So let's start the topic. Here, engineering stress and curve for ductile material. So we are going for ductile material because in our syllabus, mostly questions will be from the ductile materials only. But at the last, I will discuss brittle material also. Okay. So first of all, what is ductile material? Means ductile material is a material which can be elongated much. That means if the percentage elongation is more than 5%, then the material is known as ductile material. So percentage elongation is more than 5%. That means stretching will be more than 5%. Okay. Then it is ductile. For example, mild steel. Mild steel. And today I will draw a stress and diagram for mild steel only. Okay. So let's start here. What happened? Here we have stress and strain. On y-axis, here we have stress, and on x-axis, here we have strain. So here we have engineering strain, here we have engineering stress, or simply we can say stress and strain here we have, and here we have origin 0, 0, where stress and both are 0 like this only. Simply just like x-axis and y-axis, just like school level mathematics. Now what happened? This test done on UTM machine in your lab machine. You all have seen UTM machine in your college in the lab, that is universal testing machine, and universal testing machine we are going for the tensile test of the specimen. We are going for the tensile test on the specimen. Suppose we have a rod, and for that rod we are going for machine UTM machine, and UTM machine used to put a tensile load, on this rod, and so many readings were noted, and plot for stress and strain will be done on this machine only. The same thing here we have, that is the stress strain diagram. Now just look at here. Suppose what happened initially, the value of load will be 0. Suppose initially the value of load will be 0, P will be 0. What will happen to the stress? I know stress is load upon area, so it will be also 0. And what about strain? Strain will be also 0. So initially when load will be 0, stress, strain both will be 0. So here we have first point, 0, 0 will be the first point. Now what happened if load starts increasing? Because here we have gradual load. In strength of material, all the loadings are by default gradual load. Gradual load means load is not suddenly applied. Suppose load is 100 Newton. Let's say load is 100 Newton. So suddenly load is not 100 Newton. Gradually increases. Let's say 100 Newton load is here. For example, 100 Newton. So 100 Newton is not applied suddenly or instantly. Starting with the 0 Newton. Starting with P is equal to 0. Then 1, then 2, then 3, and so on. It will reach to last value 100, maximum value 100 here. So this is known as gradual load. So gradually load will goes on increasing. So here what happens, if load increases, definitely stress increases as well as strain also increases. As well as strain also increases. If load increases, stress increases as well as strain increases. So we will get a graph like this, a straight line graph. We will get like this, a straight line up to here, and this point will be A. This point will be A. Here we have point O, 0, 0, and this point is A. So OA will be a straight line. First of all, O to A is a straight line. First of all, let me tell you, it's a straight line first of all. And second thing, point A is known as proportional limit. Point A is known as proportional limit. So whatever I am telling to you, please go through this in very seriously, because whatever questions will be asked in the examination, whether it's very difficult or easy, I will be telling each and everything. So go through these things very seriously and try to understand in the best way. Do not go to mug up all the points and things. Otherwise, there is no use at all. Okay, because GATE exam is not an exam where you can mug up so many formulas and you can able to solve any problem and you will be topper. No, GATE exam is exam where you can build your concepts, then you can able to try questions in exam, then you will be topper. Okay, here we have proportional limit. So what is the meaning of proportional limit? So proportional limit means Hooke's law valid here, that is stress directly proportional to strain, or I can say stress is equals to Young's modulus into strain. This thing is valid up to this point only. This thing valid up to this point only. Valid up to point A. Valid up to, right, valid up to point A. Up to point only. That means this Hooke's law will be valid up to point A. Beyond point A, this is not valid. Okay. So here we have proportional limit. Now, further load increases, then graph will be like this. Then here we have point B, which is known as elastic limit. Point B is known as elastic limit. So here we have elastic limit point B. Okay. So here we have elastic limit. I am writing here that point B is known as elastic limit. So what is the meaning of elastic limit? Very simple. Elastic limit means the point or the last point up to where material can regain 100% after unloading. 100% recovery, 100% recovery up to this point. 100% recovery up to this point, up to this point. Suppose what happen if we apply load beyond the elastic limit, then if we remove the load, then 100% recovery is not there. Maybe partial recovery can be there, but not 100% recovery. But here, if we apply load up to the elastic limit or within the elastic limit, then what happen? 100% recovery will be there for strain in the body. Okay. Okay. So here we have elastic limit. Now, if we further increase the load, then what will happen? If we further increase the load, then what will happen? We will get another point which is known as here, which is known as C point, which is known as upper yield point. Then we have D point, which is known as lower yield point. Then this curve will be like this. So here we have a point D, lower yield point. Here we have point E, that is ultimate point, and finally we are getting the fracture point F. Finally we are getting the fracture point F here like this only. Okay, so many points here we have. What about C and D point? So C and D point, upper and lower yield point. If somebody is saying what is C and what is D point, so here we have C is the upper yield point. C is known as upper yield point. C is known as upper yield point, and D is known as lower yield point. Lower yield point. D is known as lower yield point. So which point is very important? So this one, lower is very important because upper can't be noted. Upper can't be noted. So lower yield point means yield point, yield strength. Okay. Or yield stress like this only. Now what about point E? Point E is known as ultimate point. Point E is known as ultimate point. So ultimate point means strength of material. Strength of material means the maximum stress the material can withstand, or the maximum stress material can sustain before fracture. Before fracture, maximum stress material can sustain. This is known as ultimate point or ultimate stress or strength. So what is strength? Basically, maximum stress material can sustain. Maximum stress material can sustain. Maximum stress material can sustain. Material can sustain. Material can sustain before fracture. Before fracture is known as strength. Before fracture is known as strength of material. Is known strength is known as strength. Okay, very simple. Now what about F? What about F? F means fracture point. F means fracture point. Here we have F means fracture point. Here we have, that means material breaks into two pieces. It means material breaks into two pieces. Material breaks into two pieces. This is fracture point. Here we have. Now I will discuss what is yielding basically, because so many students used to confuse in yielding, that what is basically yielding. So I will explain you yielding in best and easiest way. Okay, that what do we mean by yielding here? So just look at here. Basically, what is yielding here we have. So yielding means, if I go and explain you what is yielding basically. Okay, so basically yielding means, here I am writing yielding means yielding. So what is yielding? If more strain, if more strain or more change in strain, right? If more strain with almost no change in the value stress, with almost no change in the value stress, that means if stress remains almost constant, if stress almost constant, during that time, if more strain will be there in the material, that is known as basically yielding. But why yielding is there? But why yielding? The question is why yielding in material? The question is why yielding in material, and the answer is due to, right? Due to slipping of carbon atoms in the moisture. Due to slipping of carbon atoms in the crystal structure. Carbon atoms in crystal structure. In crystal structure. In crystal structure. Since we know the steel is made up of iron plus carbon, and if carbon atom slips in the crystal structure, so these things happen, yielding happens. Yielding means if there is large change, if there is a sudden change in the length, more change in the length of the rod with almost equals means almost constant stress, then this is known as yielding. And why yielding we have, I have given you reason. And one more reason also for why yielding, because slipping, because right, slipping along 45 degree, slipping along 45 degree in the rod. Suppose here we have rod and tensile force is applied on this rod, tensile force applied in this rod like this only. Here we have tensile force P. Here we have tensile force P. Now what happened? If here we have tensile force P, so this is the plane at 45 degree. Let's say this is the plane at 45 degree. So on this plane, maximum shear will be here. On this plane, maximum shear will be here on this plane, or maximum shear, it is also known as maximum slip. Maximum slip of this plane. Maximum slip. Due to this, because of the slipping, what happened? There is a large change in the value of length. There is large change in the value of strain without any significant change in the value of stress. That is known as yielding. So we come to know what is yielding as well as why we have yielding. Okay. Now here we have one more point, that is here from D to E. This reason D to E is known as, so from here D to E, just look at here. D to E is here, from D to E, this point D to E. This reason is known as strain hardening. This reason is known as D region. D region is known as strain hardening region. This region is known as strain hardening region. Strain hardening region, here we have this one is strain hardening region. And what is the meaning of strain hardening? Basically, strain hardening basically, if suppose here we have cold working, that means this material is at room temperature and load is applied to stretch the material, to stretch the rod. So what happened after a certain value, that means after yielding, at D point it is yielding. After yielding, what happened? The behavior of material suddenly changes and material starts offering more resistance. Means material offer more resistance. Material offer more resistance in yielding. More resistance means more stress. That's why the value of stress goes increasing from here to here to here to here. And finally here we have maximum stress value, which is known as ultimate point, which is known as maximum stress, sigma max, ultimate point here, right? Sigma ULT, ultimate stress, which is also known as strength, here we have. Okay. And F is the fracture point, and necking starts here, at point E, because E is the highest point na? So necking starts at point E. Basically what happened, necking starts at point E. What is the meaning of necking? Necking means, suppose if here we have material, load is applied here na? So after some time what happened, after some time, suppose we have metal, after some time this will be the condition. After some time this will be the condition like this here. If load is acting here, if load is acting on the same space, so after some time here area reduces. Here sudden reduction in the area here at this point. This one is known as necking. So here here it is known as necking. Neck or necking. Just like human being, you can see your head, right? Head size is large, your body shoulder size is large, but in between head and shoulder, neck is a very cross section of neck is small. Here just like, so if we stretch the bar, if we stretch the rod, so somewhere it will be possible, somewhere it will be there point where cross section area will be drastically, means more change in the cross section area, or drastic change in the cross section area, or significant change in the cross section area, which can be seen by the naked eyes. That point is known as necking, and this necking starts at the ultimate point only. So we can come to know during the in the lab, if you will in the third semester. So if you have done this experiment in the lab, if necking will be seen, then you come to know that material will break from there only. So here we have stress strain curve. So point A is the proportional limit first of all. Okay, point A here. I explained you all the points. In exam we have 1 marks question from theory. Point A here we have a proportional limit. Point B here we have elastic limit. Point C here we have upper yield point. Point D here we have lower yield point. Point E here we have ultimate point, and point F here we have fracture point. So please remember name of all the points here. Okay, and here from B I can say, from here B I can say this zone is known as elastic zone. Here this zone is known as elastic. So from here to here this one is known as elastic zone. Elastic zone here we have, and this zone from here to here, this one is known as, because after elastic zone here we have plastic zone. Here we have plastic zone, here we have plastic zone, here we have elastic as well as plastic zone, here we have. What is the meaning of elastic? Up to that point, if we remove the load, 100% recovery will be there. That means material will come back to the original position, original state. Okay, 100% recovery. Suppose the length of the initial bar is 10 centimeter, and after stretching, length will be 12 centimeter. If we remove the load, length again becomes the same, that is a 10 centimeter. That is known as 100% recovery. That is known as 100% recovery. So we have come to know that what is stress strain diagram. So how stress strain diagram can be drawn for this ductile material. And this stress strain diagram is drawn only for one material, that is mild steel. Do not forget whatever stress strain diagram right now you are seeing on the screen is only for the mild steel, that is the ductile material. There can be so many ductile material, but here I am showing you the stress strain diagram for the mild steel, and this is the only very important diagram asked in gate examination, whether you are from mechanical as well as civil. Okay, so we have seen all these things, all the points here we have done. Now what happened here, we have seen for ductile material. Now for different material we can have different. So we are going for the different types of stress and diagram. So many times questions asked from this topic in gate examination. So let me draw. Suppose if this type of diagram will be here, if this type of diagram will be there for stress and curve here, suppose here we have stress and here we have strain. So this is known as linear elastic. This is known as linear elastic. This curve is known as linear elastic curve. So many times this type of small diagram came in gate examination in previous year question PYQ. So please remember. Suppose if this type of thing will be here, this type of thing, linear elastic with perfectly plastic. So here we have linear elastic. Here we have linear elastic with perfectly plastic. Perfectly plastic. Perfectly plastic. And here suppose stress strain. So this is perfectly plastic. This is perfectly plastic. This is perfectly plastic here. And suppose if here we have like this, suppose here we have like this, here we have linear elastic, and then like this only strain hardening. If it is going with some particular angle, not horizontal, here if after this point if it will become horizontal, just look at here in this second diagram, this is only perfectly plastic horizontal, but this is not horizontal. Just look at it, this is at an angle theta. So this is not horizontal. So that's why if inclined line will be somewhere here, it is known as strain hardening. So this one is known as linear elastic with strain hardening. Linear elastic. This one is linear elastic with strain hardening. With strain hardening. Strain hardening here we have. Strain hardening here we have. Okay, and suppose if here we have, a diagram like this, and suppose I am saying that this is for right y-axis. Suppose if here we have line on the y-axis, if here on the line we have y-axis, that is for sigma and is right epsilon. Here we have stress and strain like this, and here we have, suppose here we have one diagram for stress and diagram for the steel, because mostly question will be asked from there only. And here this small diagram, please remember the name of the small diagram, because so many times asked in the previous gate examination. Okay, now we will move ahead. Now we will move ahead, and we'll go for some other material also. For example, for brittle material, if somebody say what will happen to the brittle material, yes, definitely I can say for brittle material how we can draw. Just look at here for brittle materials. Suppose we are saying for brittle material how will be stress strain diagram. Brittle material. So for brittle material directly fracture point will be here we have. For example, brittle material directly we are going for the fracture point F. Directly we are going for the fracture point F for the brittle material. And suppose if carbon percentage changes in this, This one is for the brittle material. Na? And suppose here we have for mild steel. Let's say here we have for, let's say here we have for mild steel. MS. I'm writing MS mild steel. And what is the percentage carbon in the mild steel? Almost 0.3%. 0.3% carbon. 0.3% carbon. 0.3% carbon in the mild steel. If suppose percentage of carbon increases, then what will happen? Then what will happen if percentage of carbon increases? So this will be like this. Suppose 0.6% carbon, and suppose here, if here it will be okay. So then here will like this. Then here will like this. Like carbon increases. Suppose here we have 0.8% carbon. Okay, 1.2% carbon like this only. So, or 1% carbon like this only. So if carbon percentage increases, so what happen? If percentage carbon increases, then what I can say? Hardness increases. Hardness increases, ductility decreases. Ductility. So many theoretical question of 1 marks. Ductility decreases. Hardness increases, ductility decreases. Ductility decreases means toughness decreases. Toughness, toughness decreases. So if we are increasing the percentage of carbon in the steel, percentage of carbon in the steel for any type of, if we have steel and we are increasing the percentage in the carbon, percentage of carbon in the steel, definitely hardness increases, right? That means brittleness increases, but ductility and toughness decreases for that steel. Okay. Okay. Now we will go for resilience as well as toughness. So what is resilience and toughness? Just look at here. If we are going for the resilience, then what do we mean by resilience here? Very simply, resilience and toughness both are almost same, but little bit difference here we have. Suppose what happen if we stretch a rod? If we stretch a rod, then what happens? Some work has to be done in stretching the rod. So that work will be stored in the rod as energy, potential energy, which is also known as strain energy, and that is known as resilience. That is energy store. I can say energy is stored in body. Energy is stored in body due to strain or due to stretching. Okay, energy is stored in body due to strain, because we have strained the body now. We have applied the force to strain the body. So energy is stored in body due to strain up to elastic limit. Up to elastic limit is known as resilience here. Like this, suppose uh, here we have, let's say, point B, elastic limit. So suppose if we have loaded here up to this point only, so this will be known as resilience. This area will be known as, this area will be resilience. This area will be resilience. And what about maximum resilience? Right, proof resilience. What about proof resilience? If I say proof resilience, so what is proof resilience? What is proof resilience? That is the maximum resilience, which is also known as maximum resilience. So maximum resilience will be up to the elastic limit, will be up to the elastic limit like this only. If here we have point B elastic limit, so up to here only, maximum energy stored in the body at elastic limit. Maximum resilience or maximum is stored at elastic limit, at exact at elastic limit, at elastic limit, at elastic limit like this only. So this will be known as proof resilience. This will be known as proof, and one term is modulus of resilience. One term is modulus of resilience. Modulus of resilience. So please remember, remember all three terms. They are very different from each other. Otherwise, 1 marks question will be coming in the examination, GATE examination. You will be confused which option I should go and tick, whether resilience, whether proof resilience, or whether modulus of resilience. So what is modulus of resilience? That is proof resilience. That is proof resilience. That is proof resilience divided by proof resilience divided by per unit volume. Means proof resilience per unit volume is known as model of resilience. Unit will be joule per meter cube or joule per mm cube. Joule per mm cube. For all, joule per meter cube, joule per mm cube like this only. So here we have resilience means energy stored in the body up to the elastic limit at any point. But what is proof resilience? That is maximum resilience, Energy stored exactly at the elastic limit, which is maximum resilience. And what is modulus of resilience? That is the maximum resilience, that is proof resilience per unit volume is known as modulus. So please remember all three words: resilience, proof resilience, and modulus of resilience in very clear way. Otherwise you will be in problem. And what about toughness? And what about toughness? If you go for the toughness, toughness means very simple. Toughness means energy. If you are going for the toughness now, that is basically energy store up to fracture point. So I can say here energy store up to fracture point, that is known as toughness. And the other definition of toughness is ability of material to resist the impact load basically. Okay, so here, suppose here we are stress strain diagram. So suppose here we stress strain diagram, and this is the fracture point F. So whatever energy is stored here, whatever, this area will be equal to toughness. This area will be equal to toughness. This area, right? Numerical came in gate examination already. So in that numerical, we do not do anything, just we calculate the area, and that is known as toughness or modulus of toughness in terms of joule per meter cube. So this area will be toughness or modulus of toughness. That means energy stored in the body up to the fracture point only. But in resilience, it is up to the elastic limit only. Okay. Okay, students. So in this lecture, I have covered stress strain diagram in very detail, and definitely no need of any paid lecture also. Definitely for stress strain curve only, you can go through this video and you can able to solve any problem of stress strain diagram in your subject strength of material in your coming gate examination. Suppose if you are preparing for the next gate examination, that is gate 2025 or gate 2026. So definitely by watching this video, you can able to solve problems in the gate examination, whether you are from the mechanical engineering or you are from the civil engineering. So let me tell you one thing. This is a series of videos here on this GATEFORUM YouTube channel. I am providing you this video, this series of video here. Today we have lecture number 3rd, then you can go for lecture number 4, lecture number 5 also. Okay, so I am providing videos of strength of material in this series. This will help you out, but this is not a full course, this is not a paid course, because full course, paid course can't be done within a half an hour, 1 hour, 2 hour. In paid courses or full courses, lecture will be of 2 hour, 3 hour, 3.5 like this only, and so many hours we used to go for the subject, then we can able to complete the subject. Okay, so this is a just trial that how good we are teaching on GATEFORUM, and how well we can help you out if you prepare with us. Okay, so definitely if you if you find this video as very helpful to you, so definitely like the video, subscribe this YouTube channel, the GATEFORUM YouTube channel, and please share this video with your friends also. So please like, subscribe and share. And if you have any question or query regarding this topic, definitely put your comments in the comment box of this YouTube channel. I will be personally replying you. Okay, so bye all of you, and we will meet in the next lecture. And in the next lecture, that is in the lecture number 4, I will be starting Mohr circle. In the next lecture, I will be starting Mohr circle. Very important topic of strength of material. So please watch next lecture also, and please watch all the lectures to get very good concept of strength of material. Okay, so we will meet in the next lecture, next video, lecture number 4, with the new topic, Mohr circle. Okay, students. So thank you all of you. Bye. We will meet in the next video. Okay. Bye all of you.